Hi guys, in this video we're going to talk about buffers. First off, let's just define what a buffer is. It's a solution that resists change in pH. And more particularly, this solution has to contain two components. It contains a weak acid and its conjugate base. That's really important. The weak acid and the conjugate base have to be related. And they have to be in approximately equal amounts in the solution. So a way you could make up a buffer is to basically mix equal amounts of a weak acid and its conjugate base in water, and that's going to now be a buffer solution. So an example, if I mix 1 mole of acetic acid, which is a weak organic acid, plus 1 mole of the conjugate base, something like sodium acetate. These two are related as the acid and conjugate base pair. And that's a really important point about buffers. You can't just mix any random acid and any random base and come up with a buffer. It has to be the acid, a weak acid, and its conjugate base. So if I were to mix those in solution, this would give rise to a buffer solution called the acetate buffer. Now in the next section, I'm going to list out a variety of buffer systems that you might commonly encounter. So let's take a look at some combinations of acids and conjugate bases that you might run across. So I'll just call this some common buffers. And let's just take a look at these in terms of the HA, which is the acid component, and the conjugate base. So in this first example, I have acetic acid, like I had in the previous section, and its conjugate base, called acetate anion. Now if you mix those two in approximately equal amounts and then you measure the pH. So over here in this column, what I'm going to list is if we now mix these in equal amounts, put a pH probe into solution and measure the pH, what would that pH come out to be? Well, it turns out it would be 4.74. So that would be the pH of this equimolar solution containing both acetic acid and the acetate anion. Okay, another example is this one. This is called the carbonate buffer. So here I have carbonate, H2CO3, and I'm going to mix its conjugate base, the bicarbonate ion. If I mix those in equal molar amounts, the pH, if I were to measure that, would be 6.30. Next example, I have the phosphate anion. So this is actually dihydrogen phosphate. It has a single minus charge. If I pull off one of those protons and I get the monophosphate dianion, these two again are conjugate acid and base pairs. The pH of that solution, if they were mixed in equal amounts, would be 7.21. Last example, I have the ammonium ion, NH4+, and its conjugate base, which would be ammonia. Mix those in equal amounts, measure the pH, 9.25. Now, these base or acid-base pairs, these buffers, are often referred to more often than not by one of the names of the components here. So in this case, this is called the acetate buffer. This would be the carbonate buffer. This would be the phosphate buffer. And then lastly, this would be the ammonium buffer. But in reality, when we talk about an acetate buffer, it's not just acetate that's there. It also has to be its conjugate acid. And that holds for all these. Now, one of the really interesting things about this is that if you look at the pH of these solutions, it turns out that if these are mixed in equal amounts, the pH that you measure of that solution actually equals the pKa of the acid in that buffer system. So this value actually represents the specific pKa value for acetic acid. Likewise, 6.3 would represent the specific pKa for one of the protons of the carbonate, or of carbonic acid. In this example, one of the protons of dihydrogen phosphate its pKa. Again, if these are mixed in equal molar amounts, the pH of that solution equals the pKa of that. And then lastly, 9.25 would represent the pKa of the ammonium ion. So this relationship of pH and pKa now is sort of combined together when we look at buffers. The key here is that if we are looking at the pH of a buffer solution where we have equal molar amounts of an acid and its conjugate base, the pH will equal the pKa of the acid component. So let's take a look at what's really going on in a buffer system. In the previous section, I mentioned that when you have equal molar amounts or equivalent amounts, so when the ratio of HA to A minus equals 1, that's a situation where you can have a good buffering system. So if I were to draw out a titration curve where I'm going to measure the pH of a particular solution, and I'm going to add moles of NaOH. And the specific example that I'm going to look at is the acetate buffer. What you would see is when you have no sodium hydroxide present, you would get a curve as you add sodium hydroxide that ends up looking kind of like this. Okay, and we won't go all the way out to lots of NaOH, but here I would add 1 mole, let's say, of NaOH. But I have 1 mole of acetate, or I'm sorry, acetic acid, and 1 mole of acetate in my buffer. Okay, so those are the conditions of my buffer. And if I, again, am measuring the pH, what I'd find is that as I start adding 1 mole of NaOH, I get this sort of plateauing effect, where the pH is not changing very much. Well, it turns out that if I now have an equal molar amount of these two components in my solution, and what I would be doing in this diagram, this situation is satisfied right here. So if I were to start with just acetic acid, and the pH of acetic acid is down around 1.5, so if I had a pure solution of acetic acid and I now started adding 1 mole of NaOH, what I'd be doing is converting this acetic acid into a 50-50 mixture of the two components. All right. So to actually match up with this, I'd actually have to start with 2 moles of acetic acid in my initial solution. So if I added 1 mole of NaOH to 2 moles of acetic acid, I would get to a point where I would now have equal molar amounts, 1 mole of acetic acid, 1 mole of acetate anion. And it turns out that when that situation occurs, the pH equals the pKa of my acetic acid. So this would have a pH value of 4.74. And this pKa value, again, is the pKa value of the acetic acid proton. So this region where it's relatively flat then, this is the so-called buffering region. Okay, so if I'm sitting right here at this place on the curve, notice if I were to add a little bit more base, my pH would not change very much. Conversely, if I were to add a little bit of hydrochloric acid to this, I would go back this way. Again, the pH would not change very much. So this is what's actually going on in a buffer system, is essentially because you have both the acid and the conjugate base forms, it's going to now resist change in pH because of this plateaued region called the buffering region. All right. Now, in general, a buffer can be effective at about plus or minus 0.1 pH units relative to the pKa. Okay. So if I went up to 5.74 or down to 3.74, I would still be in a region that could potentially be a buffer. In reality, usually these are closer to values of 0.5 pH units relative to the pKa, where it's a good buffer. But we're just going to say a value of 1, plus or minus a value of 1. So if I had an acetate buffer like this one, and I know the pKa is 4.74, if I actually measured a solution where I've added some acid or base, and let's say it's down at, let's say 4.0, that solution still has a significant amount of the conjugate base pair that it still could resist a little bit of pH change. All right? So that's the basics of how a buffer actually works. In the last section, I'm just going to briefly mention the carbonate buffer system that we find in blood. So in this last section, I want to talk about a specific buffer called the carbonate buffer. This is one of the buffers that you find in your blood that helps keep the blood at a relatively constant pH. So this buffer involves the following two species: carbonic acid, which is H2CO3, and its conjugate base pair called bicarbonate anion, which is HCO3 minus. So these two components now are in approximately equal amounts in the blood, and that's going to actually be determined by this equilibrium. So when water is saturated with carbon dioxide gas, carbon dioxide has a little bit of solubility in water, and it can actually combine to form this bicarbonate anion. Okay? So depending on the saturation of your blood with CO2 gas, that's going to affect how much bicarbonate is present, and then there's an equilibrium that's set up between the carbonic acid. So if these two are present in approximately equal amounts in the blood, we get blood that's now buffered that has a pH of around 7.4. So 7.4 is often what we refer to as physiological pH. Now, if the blood pH happens to become more acidic, so if this buffer shifts more towards the carbonic acid form, so down around 6.8, this is called an acidotic state, or acidosis is what it's often referred to in the medical realm. Oop, that came off the screen. Let me write that over here. We'll just write it right here. Acidosis. So if the blood pH drops well below 7, down to around 6.8, the blood is called acidotic, or the patient would have a blood acidosis. Conversely, if the pH in the blood were to increase, and we're now shifted more towards the bicarbonate anion, this would now have usually a pH of around 7.8 or greater, and that's called alkalosis. Now, this buffer is, again, directly linked now to this little side reaction in terms of CO2. So if there is a saturation of CO2, so if more CO2 gets put into water or in the blood, we're going to be pushing this equilibrium more towards the left, and that would lead to an acidotic state. Conversely, if CO2 is sort of somehow brought out of water, it's going to pull things towards the right, and that would now give a more alkalosis type state for the blood. Now, you guys will learn a lot more about this as we go through the semester and probably in some of your other classes, but this is a really important one, important medical buffer. All right, I hope those concepts help explain buffers. Good luck.